Welcome back to matrices. We are going to talk about something called Cramer's rule in this video. It's going to be another technique for helping us to use matrices when we are solving systems of equations. Now, in order to explain how Cramer's rule works, I'm going to first focus on a system of equations and think about what we might do when we're using elimination to solve the system. Okay. But before I do that, let's just think about this for a second and how you might write this using matrices. Like if you were initially, a couple of videos ago, if you were initially working on this matrix and you're wanting to try to set up an augmented matrix to solve the system, you would set up something that looked like that, where you used your coefficients and your constants in the matrix, and then you would try to get that matrix down to having that diagonal of ones and then the zeros above and below the diagonal. But we're not going to do it that way right now. We're going to actually incorporate what we recently learned about determinants to help us with this matrix. So quick side note, let's take this matrix and let's rearrange things a little bit. And when we do, we're going to look at the determinants. Okay, let's take this matrix and let's just look at taking the determinant of the coefficients for the equations, not those constants. If we do that, we'll have negative 8 minus 3, which is negative 11. And it'll make more sense in a minute, but we can also take this matrix and in place of where the x coefficients are, the 4 and the 1, we can put those answers and then keep the 3 and the negative 2 where they are. And we can look at the determinant of that. 2 times negative 2 is negative 4, minus 15 is negative 19. This will all make sense in a minute, just bear with me. And then for determinant sub y, we'll leave the x numbers alone, and in place of the y numbers, we're going to put those answers and do the determinant of that. 4 times 5 is 20, 1 times 2 is 2, 20 minus 2 is 18. Okay, so keep this in your mind. Keep this in your little pocket of information that we're going to use later. So notice that, okay, so the initial capital D, that matrix, we're doing the determinant of just the piece that had the 2 by 2 that had the coefficients. Then the D sub x, we were doing the determinant where we put the 2 and the 5 answers in place of the x coefficients, but left the y coefficients alone. And the D sub y, we left the x coefficients alone, and then replaced the y coefficients with the 2 and the 5. And we found determinants, in all three cases. Okay, so come back to that in a minute. Let's take a little look real quick here at using elimination to solve this system. So we're going to go way back several lessons, back to like college algebra. And we're going to look at solving these by elimination. Now let's say to do that, we take the first equation and multiply by the coefficient in front of y on the second equation. So you end up with negative 8x minus 6y equals negative 4. And let's say we take the second equation and multiply by the coefficient in front of y on the first equation. But the negation of that, sorry. I'm supposed to use the negation in this case. So we got negative 3x plus 6y equals negative 15. All right, so now we're all set. We can do our addition. Okay, and when we do our addition, we have negative 8 minus 3 for the x. The y's cancel out, these come out 0. And then we have the -4 and the -15 for that over there on the other side of the equal sign. So we have a -11x equals -19. We divide both sides by -11. We end up with 19/11ths for the x value. And of course we can go back and plug in 19/11ths for x and try to find y. So that is an option there. But take a closer look for a second. Take a look. Let's go back to those matrices I said to put in your pocket. Let's pull them out and let's look at them for a second. Notice that this -19 here with d sub x is right here. And notice that this -11 with d is right here. So when we solved for x, we were able to take that determinant sub x over that determinant without the subscript. And if you use generic like a sub 1, b sub 1, a sub 2, b sub 2, you can prove that this is a technique that will work over and over again. And the very interesting thing too is that similarly, you can find y by doing d sub y over d. So that would be 18 over -11 or -18/11ths. So if you went ahead and went in and plugged the -19/11ths in, you would get that answer. Pretty cool, huh? It's pretty neat how that works out, right? So that's a new tool now. It's called Cramer's rule. All right, so you're given the system, so Cramer's rule for 2 equations in 2 variables. So you're given the system a sub 1x plus b sub 1y equals c sub 1. And a sub 2x plus b sub 2y equals c sub 2. And as long as capital D is not 0, because that wouldn't work. If it was 0, you divide by 0, that's undefined. That's not going to work. Then the system has unique solutions, d sub x over d and d sub y over d for x and y. D is the determinant of the matrix A1, B1, A2, B2. So that's those coefficients in front of x and y. D sub x is the determinant where you put C1 and C2 in the x column and keep B1 and B2 in the y column. And d sub y, you keep A1, A2 in the x column and then put C1, C2 in the y column. Now, really quick, if you find D and it equals 0, then Cramer's rule does not apply. Because notice that would end up putting a 0 on the bottom of a fraction. That's not going to work. So in that case, the system is inconsistent or has, infinite solutions. Infinitely many solutions. Okay, so let me show you an example where you can just stop when you get D is 0. Let's say you have the system x minus 3y plus 2z equals 5, 3x I'm jumping a little. I had said 2 equations, 2 unknowns. You can expand this and have 3 equations, 3 unknowns as well. Where D, D and it's the same kind of idea. Where D sub x or x is D sub x over D, y is D sub y over D, z is D sub z over D. You're doing your determinants all the way down. And you're still doing the same kind of thinking as far as what determinants you're finding. I'll show you. All right. This was just a good example to show you when you don't have to go any further. Like for this one, let's say you just want to find D. You're finding the determinant when you have 1, -3, 2, 3, 1, -4, -9, -3, 12. So remember, I'm finding the determinant in this case where all the coefficients of x, y, z. So I just expanded it. Now it's a 3 by 3 because I have 3 equations, 3 unknowns. It has to be an n by n system. It has to be a nice little 3 by 3 kind of situation. It has to be in this kind of form with x, y, z or x, y or whatever. And now from here, let's just do that determinant. Let's see. I think I went ahead and used row 1. So I can do it's plus, negative, plus. So I had +1 and then determinant of 1, -4, -3, and 12. And then minus 3, so +3, determinant of 3, -4, -9, and 12. And then +2, determinant of 3, 1, -9, -3. Okay. So I have 1 times 12 minus -12 plus 3 times 36 minus 36 plus 2 times -9 minus -9. So that's 1 times 24 plus, something went wrong there. 12, oh, that's 12 minus plus 12. Sorry. So that's 1 times 0 plus 3 times 0 plus 2 times 0. So it's a big fat 0. So can't use Cramer's rule. Then you can just stop and say, well, let me look at this another way. Maybe I'll be able to figure out what's going on. And actually, if you take this equation and divide through by -3, you end up with 3x plus y minus 4z equals 8. So you end up where these two are actually the same. So then you know you're dealing with infinitely many solutions. So you can't use Cramer's rule to try to narrow it down to one single point, one ordered triple. But anywho, all right. So back to general form of Cramer's rule. As long as that's not 0, that D. You can have some kind of system, n by n system. And the equations are the form a sub 1 x sub 1 plus a sub 2 x sub 2 plus a sub 3 x sub 3. You know, to some a sub n x sub n equals b. As long as you have those, D is determinant of n by n matrix with coefficients of the variables. I should say with all coefficients of the variables. And then we know D can't be 0. d sub x, determinant when replace, or d sub x1, or d sub x, determinant when replace entries in D. Like column 1 of D. So D is like D sub x1. Column 1 of D gets replaced with x sub 1 coefficients. Like D sub x2, you're going to replace column 2 of D with the x sub 2 coefficients, and so on. So you're going to still get x sub 1 is d sub x1 over d, x sub 2 is d sub x2 over d, and so on. So d sub xn over d for x sub n. So same idea as 2 by 2, it's just you're expanding it. So all the coefficients for x sub 1 will get replaced by those b values in d sub x1. The coefficients for x sub 2 will get replaced by those b values in the x sub 2 coefficient column, and so on. And then you'll still do those little ratios to get your values. All right, so let me do one that actually comes out that's 3 by 3. So one we did earlier wasn't going to work because D was 0. Let's do one that works. Let's say you have the equations 2x minus 4y plus z minus 19 equals 0. Keep in mind we also need this to be in a standard form. So we really need it to be 2x minus 4y plus z equals 19. So it might help you to rewrite that to make sure you get the signs right. 4x plus 6y minus z plus 15 equals 0. So let's rewrite that as 4x plus 6y minus z equals negative 15. X plus y plus 2z minus 11 equals 0. So x plus y plus 2z equals 11. And just pausing here for a second to double check, make sure I copied everything correctly. It's so easy to miscopy a sign or something. All right, so for this, capital D, I'm trying to find the determinant when I take all the coefficients of the x, y, z's and make a little matrix. So 2, negative 4, and 1, 4, 6, negative 1, 1, 1, and 2. Let's say that I use row 3 to do this. I've picked row 3 because of the 1s. I thought that made it a little, looks like it might be a little easier. And then, remember my signs, plus, minus, plus. So I'm going to have 1, and then minus 1, and then plus 2. So for when I'm looking at row 3, like when I do the 1, I'm ignoring everything in the same row and column and then making a new matrix with that. When I do the negative 1, I'm ignoring everything in that same row and column, doing a matrix with that. And then like when I do the 2, ignoring everything in that same row and column, and doing a matrix out of that. And then doing those determinants times the elements in row 3. So for the first one, I've got 4 minus 6 is -2. -2 minus 4 is -6. 12 minus -16 is 12 plus 16, or 28. So I've got -2 plus 6 plus 56 equals 4, 56 equals 60. All right, so I got to keep that in mind. So capital D is 60. All right, D sub x. So I get to take the 19, the -15, and the 11 and put that in the column where the coefficients of x were. Then the coefficients of y stay the same. Coefficients of z stay the same. So I'm going to be trying to find straighten that out, because I'm really just trying to find the determinant of this. All right, so I think for that one I used column 3. So it's plus, minus, plus. All right, so for 1 times determinant of that, minus, minus, will be +1, determinant of that, and then +2, determinant of that. So determinant of the elements that are not in that same row and column. So I've got 1 times -15 minus 66 plus 1 times 19 minus negative, so plus 44, and then plus 2 times 114 minus 60. All right, so 1 times -81 plus 1 times 63 plus 2 times, what, 54? So -81 plus 63 plus 108. -18 plus 108. That equals 90. So D sub x comes out to be 90. All right, 2 more. D sub y. All right, the 2, the 4, and the 1 get to stay the same. The y column gets replaced with 19, -15, and 11. The z column stays the same. Oops, sorry. My z column was off there. My eyes were looking at the wrong thing. Sorry about that. Okay, that's why I keep keep looking back over my stuff as I write it down and making sure I copy things correctly. All right, I'm going to use column 3 again. So we got plus, minus, plus. So we've got 1, and then we're using 4, -15, 1, and 11. Then we got +1, because negative is plus. 2, 19, 1, and 11. And then +2, 2, 19, 4, and -15. So 1 times 44 plus 15, plus 1 times 22 minus 19, plus 2 times -30 minus 76. So 59 plus 3 plus 2 times -106. So that's -212 there. So -212 and 62. So I get negative 150 for this one. All right, and then d sub z. Woo! Almost there. We get to keep the x's column the same. We get to keep the y column the same. And then the z column gets replaced with 19, negative 15, and 11. And then I think I used row 3 here because of all the ones. Ones are so much easier to work with. So row 3, where signs are plus, minus, and plus. So we have the 1 with negative 4, 19, 6, and negative 15. Then we have the minus 1 with 2, 4, 19, negative 15. And then we have the plus 11 with 2, negative 4, 4, and 6. So 1 times 60 minus 114 minus 1 times negative 30 minus 76 plus 11 times 12 minus negative, so plus 16. So 1 times negative 54 minus 1 times negative 106 plus 11 times 28. So we got negative 54 plus 106, so that's 52, and then plus 11 times 28. So 28 and 28, you get 308. So you add those up, and you get 360. All right, quick recap. So our capital D was 60. Our d sub x was 90. Our d sub y was negative 150. And our d sub z is 360. All right, so if we want x, then what do? We do a little ratio. We do d sub x over d. So we do 90 over 60, which reduces to 3/2. If we want y, we do d sub y over d. So that's negative 150 over 60. So that reduces to negative 5/2. And if we want z, we do d sub z over d. So that's 360 over 60. That reduces to 6. So our solution set is the ordered triple, 3/2, comma, negative 5/2, comma, 6. So there's the solution to that 3x3 system. Now you've learned other techniques for solving 3x3s, including, substitution and elimination combination in college algebra. But now you have something called Cramer's rule with matrices that can allow you also to solve that system. Or you could have set it up like we did in previous videos and figured out and done the Gaussian elimination type methods. Gauss-Jordan elimination, or Gaussian elimination. You could have done that too. So you're just learning all kinds of techniques. Right now, as far as what technique you use, go by what the directions say. Learn all of them. Learn how to do them all. Because when you're tested, you're going to have to know different techniques. But later on, when you're actually having to use these, what technique you choose just depends on the problem you're solving and what's easiest or what's going on with the numbers. But you've got a lot of tools at your fingertips, especially as you go into calculus class later. All right, but that is Cramer's rule right there. If you wanted to, you could plug the 3/2, the negative 5/2, and 6 back into those 3 equations, and that order triple will work in each of those equations. It'll all work out. All right. Well, we're going to be taking a small break from matrices in a way when we go to the next video. We're going to be getting into some other topics that are semi-related, and then we'll revisit matrices again later. So we haven't completely we're not completely walking away yet, but we're taking a kind of a smallish break from doing too much with matrices, and then we'll come back to them later. I think they're fun, so I look forward to revisiting them down the road. But anywho, thank you for joining me, and I will see you again soon.